Good afternoon. I'm Suresh Sethi from the University of Texas at Dallas. I came to know of this conference through Professor Greg Parlier, and I thank him and the conference organizers very much for inviting me to deliver this keynote address at this conference. I'm extremely sorry, however, that I could not come to Malta and give this talk in person. As a result, I'm coming to you via this video. Today, my talk concerns with dynamic supply chains and the hierarchical games required to model them. So we begin by looking at a very simple supply chain. In this supply chain, a supplier sets the wholesale price and the retailer orders the quantity from the supplier in order to sell the goods in the market. The supplier sets the wholesale price to maximize his profit. The retailer responds by deciding an order quantity, and he does that so as to maximize his profit. As you can see that these people both maximize their own profits respectively. However, their self-serving action do not maximize the total profit of the entire supply chain. What happens is there is an inefficiency due to this decentralization, which we call double marginalization. And the reason it's called double marginalization is because it involves two margins. The first margin, the supplier puts up a margin over his cost to set the wholesale price. And the second margin, the retailer sets the retail price by putting a margin over the wholesale price. That's why it is called double marginalization. And this particular problem is modeled as a Stackelberg game. And because of the inefficiency, there's also emphasis on finding out the contracts that will reduce this inefficiency, and we will call such a contract a coordinating contract. Before we go into Stackelberg Equilibrium, let us discuss the more popular Nash Equilibrium by John Nash, whom you might know from the movie A Beautiful Mind. In a game of two or more players, a set of decisions by the player is a Nash equilibrium if no player can do better by changing his decision while the others stay with their decisions. Alternatively, if a player can do better by changing his decision, knowing the decisions of the others and treating them as set in stone, then the set of decisions is not a Nash equilibrium. Let us now review the bar scene in A Beautiful Mind.
Incoming, gentlemen.
Aye, aye, aye. Deep breaths. Nash, you might want to stop shuffling your papers for 5 seconds.
I will not buy you gentlemen beer.
Oh, we're not here for beer, my friend.
Oh. Does anyone else feel she should be moving in slow motion?
Will she want a large wedding, you think? Should we say swords, gentlemen? Pistols at dawn?
Have you remembered nothing? Recall the lessons of Adam Smith, the father of modern economics.
In competition, individual ambition serves the common good.
Exactly.
Every man for himself, gentlemen.
And those who strike out are stuck with their friends.
I'm not going to strike out.
You can lead a blonde to water, but you can't make her drink.
I don't think you said that.
All right, nobody move. She's looking over here. Right, she's looking at Nash.
Oh, God. All right, he may have the upper hand now, but wait until he opens his mouth. I remember the last time.
Oh, yes, that was the history books.
Adam Smith needs revision.
What are you talking about?
If we all go for the blonde, we block each other. Not a single one of us is going to get her. So then we go for her friends. But they will all give us the cold shoulder because nobody likes to be second choice. But what if no one goes for the blonde? We don't get in each other's way, and we don't insult the other girls. And it's the only way we win. That's the only way we all get laid. Adam Smith said, the best result comes from everyone in the group doing what's best for himself, right? That's what he said, that's right? Incomplete. incomplete. Okay? Because the best result would come from everyone in the group doing what's best for himself and the group.
Nash, this is some way for you to get the blonde on your own. You can go to hell.
Governing dynamics, gentlemen. Governing dynamics. Adam Smith. What's wrong?
Yep, there we go. Careful, careful.
Thank you.
In the movie, Nash thanks the blonde woman for his epiphany and goes home to write his 28th thesis titled Non-Cooperative Games, where he develops the concept of Nash Equilibrium. The four friends, I suppose, act on Nash's advice, and they all choose the brunette women. The question, do their decision form a Nash equilibrium? The answer, that it is not a Nash equilibrium, since each friend could gain by going to the blonde woman while the others stay with the brunette women. So according to our second definition, it is not a Nash equilibrium. In order for me to distinguish between Stackelberg and Nash equilibrium, we will now consider a simpler version of the scene with two men, Tom and Dick, and two women, Emily and Linda. Both men prefer Emily to Linda, and no one gets any if they choose the same girl. By the way, when I was preparing these slides, my daughter says that, Papa, it is not a good idea and not a politically correct to have brunettes and blondes and the people preferring blondes. So it's better to have names. So I now have names for these people. Now, if you look at the table, we have two Nash equilibria. One is, they're both shown in purple. One is Tom, Emily, and Dick, Linda. And the second one, when Tom chooses Linda and Dick chooses Emily. If you see, in the first equilibrium, if Tom deviates for going for Linda, he suffers by getting none. Likewise, if Dick deviates by going for Emily, he suffers the same fate. Similar argument holds for the second equilibrium. Now we go to the Stackelberg equilibrium. The Stackelberg equilibrium was developed by a man named von Stackelberg, and he wrote a book, Market Structure and Equilibrium, in 1934. These are also called leader-follower games. And I also have some other big players in the game theory listed in this slide. In the Stackelberg, we will now take Tom as the leader and Dick as the follower. And it's a sequential game which is solved by using backward induction. That means first we obtain the best response function by Dick for each action of Tom, and then we get Tom's best action. So what we have seen here in these graphs, the Dick's four possible responses are shown in purple, yellow, blue, and gray. Clearly, purple is his best response function. Given Dick's best response function in purple, it is clear that Tom's best action is to choose Emily. And from Dick's purple response, Dick gets Linda. So the Stackelberg equilibrium is Tom chooses Emily and Dick gets Linda. Clearly, if Tom deviates, he loses, given the best response function of Dick in purple. And if Dick changes his response to yellow, blue, or gray, given that Tom has chosen Emily, Dick loses or stays the same. Now we will see the differences between Nash and Stackelberg equilibrium. The obvious difference is that Nash involves simultaneous decisions and Stackelberg involves sequential decisions. It is also clear that Tom has the first mover advantage because he gets Emily in this equilibrium. There's a subtle difference, and that is how we check a Nash equilibrium versus a Stackelberg equilibrium. You can see that Dick's deviation for checking the Nash equilibrium is to change his action, going from one woman to the equilibrium to another. Whereas his deviation for checking the Stackelberg equilibrium is to change his response function, going from purple to another color. There's also another difference which is not well known, and that difference will come clear when we get to slide 24. When we go from one-period games or static games to dynamic games, there are a number of possible equilibria. We will now look at only two-period supply chains just for simplicity, and we will only discuss two types of equilibria. The other equilibria are available in the literature. The first equilibrium that we will look at is open-loop solution. In an open-loop solution, the supplier announces the wholesale price in period 1 and 2 at the beginning of the game. Once this is known, the retailer's best response takes both of these prices into account and he chooses the ordered quantities in each of the 2 periods. The leader in this game continues to have a first mover advantage. The drawback in this particular type of solution is that this one does not take into account the realization of demand in period 1. Another drawback is that this solution is not time consistent. That means that supplier has an incentive in period 2 to renege on the wholesale price he announced for period 2 at the beginning of the game. He could change that price if that benefits him. So that's what we call reneging. Now, for this to work, supplier has to commit to his announced prices, and the retailer has to commit to his ordered quantities, and therefore it is also called a game with full commitment in the economics literature. Another equilibrium that we will like to consider is feedback Stackelberg solution. In this particular equilibrium, supplier announces only the first period wholesale price at the beginning of period 1. But then a solution in period 1 must anticipate what happened in period 2. In period 2, the supplier announces the second period wholesale price after observing the inventory at the beginning of period 2. The retailer responds to the supplier's wholesale price period-wise to obtain his period-wise ordered quantity. Both take into account the state observed in the second period. The solution is time consistent. There is one drawback, and it's not an important drawback, but there is one. And in this, the leader only has a period-wise first mover advantage, but not a global first mover advantage. We will now apply this model of feedback Stackelberg solution to a dynamic pricing prediction and a channel coordination with stochastic learning. This is a paper I wrote in 2015 and is published in Production and Operations Management. The paper goes and involves a cost of production, learning in cost of production. And the learning in cost of production comes through cumulative production from which the person gets experience. And this is called a learning curve. It's also called experience curve. It's called learning by doing. And one of the first examples reported for learning by doing is by Wright in 1936. And he observed that the direct labor cost of manufacturing of an airframe fell by 20% with every doubling of cumulative output. There are a number of reasons why this learning takes place, and there's a labor efficiency, better ease of equipment, improved production process, shared experience effects, etc. And there's a large amount of literature in economics on this particular issue. Our focus, however, is not into that literature, but in getting the idea that the learning effect is dynamic and stochastic. That is what we need for our purpose. And we can sort of see that the cost falls with cumulative production over time, and empirically, the rate at which the observed cost declines tend to vary widely both across and within industries, and even across departments within a firm. Particularly true for production of a new product, there will be considerable uncertainty regarding the rate at which cost will decline with cumulative production. Now we will first consider a centralized channel consisting of a monopolistic manufacturer, and the learning curve here creates the interdependency of the production cost and the cumulative production quantity. This interdependence is important because it affects our decision in the first period. Now we will assume that demand is price dependent, and we will have to have the manufacturer decide the optimal production quantity in period 1 and a period 2. And because of the learning curve, it so happens that the manufacturer might reduce price in the first period to increase the demand. And because increasing demand will mean increasing production, and increasing production would mean learning, and learning in cost production, and that would lower the future production cost. When we go to decentralized channel, the problem is somewhat more complicated. In a decentralized channel, manufacturer sells through a retailer, and the retailer has a pricing power and makes ordering decisions. And there is a double marginalization because the higher price in the first period implies a suboptimal production, and because the suboptimal production, learning effect is not fully realized. So in this particular problem, because there is inefficiency due to double marginalization, we will also look into finding a coordinating contract that achieves that removes the inefficiency of the decentralization. Here, as you can see, the manufacturer will have decision to make, and his decisions involve wholesale price and production quantity, and the retailer will respond by setting the retail price and the ordering quantity. We have a two-period model problem. We will have assumptions, and we will then look at a problem with no inventory option. The paper contains a problem with inventory option, but we will not have the time to get into that. We will then present the centralized channel, then we'll discuss the decentralized channel, and finally we will come up with a coordinating contract. In a two-period problem, the first period is interpreted as an infant stage in which the learning takes place, and the second period is the mature stage in which there is no learning in this particular setup. The demand parameters are as follows. AI is the market potential in period I, B is the price sensitivity, PI is the retail price in period I, and WI is the wholesale price in period I. There are cost and learning parameters. C1 is the production cost in period 1. C2, which is the big C2, is the random production cost in period 2, which is not known in period 1. But in period 2, it will be realized, and when it's realized, we will denote it by lowercase c2. The lambda is the random learning rate, which is a random variable. And the production variables are small qi is the retailer's order quantity in period I, and the big qi is the manufacturer's production quantity in period I. The sequence of event is as follows. Two-period learning curve model. The first period, as we call, is the infant stage where the learning takes place, and the second period is the mature stage. In the beginning of the period 1, both manufacturer and the follower observe the cost of production, which is C1. After they observe the cost of production C1, manufacturer announces the wholesale price W1 in period 1 and a production quantity Q1 in period 1. Given these quantities, the retailer then decides on the retail price P1 and order quantity Q1. Then the learning takes place, and at the beginning of period 2, big C2 is realized as small c2, right, as you can see here. And after both people observe the C2, and then observing that, the manufacturer will decide the wholesale price and the production quantity in period 2. After that, the retailer will respond by deciding the retail price P2 and ordering quantity Q2. The assumptions in models are as follows. We will assume a linear demand, deterministic demand, which is DI equal to AI minus B times PI. As you can see, as PI increases, the demand will decrease. This is called a downward sloping demand. The production cost learning will be given by a dynamic equation, which is C2 equal to C1 minus lambda times Q1. As you can see, the C1 is the initial cost, and Q1 is the production quantity in period 1, and lambda is the learning rate. So lambda times Q1 will be the reduction in the cost of production, and the C2 will be then the cost of production in period 2. Since lambda is a random variable, C2 will be realized at the beginning of period 2. The lambda, on the other hand, takes values between 0 and gamma. 0 means no learning, and gamma means maximum learning, and so the learning will be somewhere between 0 and gamma. We also assume that mean learning rate is mu and the standard deviation is sigma. We will only have the model in which no player has inventory carryover option, and so we will have a zero inventory option problem. Back orders are not allowed in this problem. Manufacturer retailers are both forward-looking, not myopic, in the sense that they don't make a decision in period 1, and then just like it's a one-period problem, then we go to period 2 and look at again as a one-period 1 problem. That would be a myopic decision-making. But here people look forward. People are forward-looking, so it is a genuine two-period problem. And we will formulate this as a Stackelberg game where the manufacturer is the leader and the retailer is the follower. There are some assumptions which are innocuous. These assumptions are basically guarantee that the price will not become negative and the cost of production will not become negative, but they can be handled if you generalize them. The centralized channels dynamic problem is as follows. There is a objective function that the manufacturer wants to maximize. The objective function is actually expected value of the profit in each of the 2 periods. If you look at the first period, it's a price times the sale. The sale is the minimum of production quantity, and the demand based on that price. So that would be the sale, and there will be a cost of production which will be subtracted from the revenue. So the first 2 terms depends on the profit in period 1, and likewise the second period depends on the profit in period 2. But in the second period, we see capital C2, which is still a random variable in the beginning. So we put an expected value, and so we are maximizing the expected profit of this manufacturer. This is a straightforward dynamic programming problem, which is easy to solve, and we can get the solution very easily, and the solution is listed here. We have a P1 star, which is the retail price in period 1. It's a retail price in period 2 is P2 star, and we have our production quantity in period 1, we have production quantity in period 2, and given all these quantities, we can also determine the profit. And the profit, of course, will be given by C1. This is the expected profit. It is a function of the initial value, so we can compute that. Then we look at the decentralized channel, which is a channel, and once again, we assume no inventory carryover. Here we have 2 different objective functions. One is the objective function of the manufacturer. The second one is the manufacturer, the retailer. And they depend on everything, all of the variables involved in this problem. And as you can see, the profit of the manufacturer is an expected value of wholesale price times the ordering quantity, which is the revenue of the manufacturer minus the cost of its production, and likewise for the second period. When you go to the retailer, we see that the retailer has a revenue which is P1 times the sale, and the sale depends on D1, P1. It's a minimum of these 2 quantities, where Q1 is the ordering quantity, and his cost is wholesale price times the ordering quantity which he must pay to the manufacturer. Similarly, in the second period, and once again, we have expected value because of the second period, C2 is random. In this setting, the manufacturer is the leader and the retailer is the follower. Once again, the dynamic equation or the bookkeeping equation is C2 equal to C1 minus lambda Q1, and C1 is given. Now, in period I, the manufacturer decisions are WI and QI, and the retailer's decisions are PI and QI. The production cost CI is the state variable in period I. Before we solve this problem, we're going to go to a general discussion of what is a feedback Stackelberg equilibrium and how we define it. And we're going to define it on a multi-period problem, so we'll assume the number of periods to be n, capital N, which is right here. In a feedback Stackelberg equilibrium, the leader determines her strategy in the feedback form as U, X, T, where X is the state at that time and T is the current time. And the follower strategy is based on the state as well as the leader's decision. So therefore, at time T, the follower's decision will be V of X, which is the state at time T. The time T is the current time T, and the decision made by the leader. And this is for each period from 1 to n. Notationally, we have to specify the leader's strategy as a U, which is a set of decisions in each period from 1 to n. Similarly, the follower strategy is V equal to decision by the follower in each period. As you can see, in each period depends on the state and the time and the decision of the leader. Now, there may be other constraints on these decisions, and taking into account all of these, we can define big U and a big V as the spaces of strategies for the leader and the follower. Now let's take any feasible strategy, U belongs to a big U, and any feasible strategy, V belongs to big V. Then that feasible solution, we should solve the state equation, which is given right here. It is xi plus 1, which is the state in the next period, is given with the state in the current period, and a function that takes the feasible decision and eventually gives you the state in the next period. If we solve that equation, we start at initial time t, where t is any time between 1 to n, and the value of the state at that time is y. So that is the initial condition starting at t. And when we solve this problem, we will have the state variable for each of the period after t. So that is defined by x, and the t sub y is the initial value at time t, so it is given as a superscript, and I is the period following a period t, and u and v are the decision we chose as a feasible solution. So xt y I u v is the state at time I going from t plus 1 to n. Given that state, we already know the decisions. So given the state and the decision in each period, we can write the profit. The profit of the leader is an expected value of the profit in each period and each period after t, and we sum the profit in each period from t to n. As you can see, there's a function pi L which gives the leader's profit. It depends on the state at time I, it depends on the decision of the leader at time I, and it depends on the decision of the follower at time I, and it also depends on the salvage value at the end of period n. Similarly, we will have a decision for the follower, and we can define these objective functions. Once we define the objective function, it is easy for us to define a feedback Stackelberg equilibrium. A pair of strategies U star and a V star, U star in U, V star in V, is called the feedback Stackelberg equilibrium if the following two inequalities hold. The first inequality says that the equilibrium solution is better than another solution where the leader deviates from U star to some value U. When he deviates U, obviously you can see that the V star, which is the leader's follower, also acts on U. So for all U in U, the first inequality, the equilibrium solution is better than the solution at any other U. Notice at this time, the V star is fixed. Then we go to the second inequality. That inequality is the follower inequality. Once again, we can say that if the follower deviates from V star to another response function V, but the manufacturer stays at U star, then for all V in V, the equilibrium solution is better than the solution with any other V for the follower as well. So basically, these two inequalities says that if leader deviates, he loses, and the follower deviates, he loses. Notice, however, that it is kind of similar to the Nash equilibrium, except the space of deviation is different than the Nash equilibrium. Now, the Stackelberg, when he defined in the single period problem, actually had it so that that U star in the second inequality can be replaced by any U, and this inequality still holds. So this is a little bit stronger than the equilibrium definition, but this strength of the Stackelberg solution in single period cannot be generalized in the feedback Stackelberg equilibrium concept. And this is the difference that I mentioned to you earlier, and this is slide 24 where we can see what the difference is between the Nash and the Stackelberg equilibrium. Next we can solve this problem by using a backward induction, and when we solve that, we can actually find out the wholesale price and the production order quantity, and then the ordering quantity, etc. Now, let us see how we implement that decision. So first we solve this problem using backward induction, and then we have this solution in our hand as a table. So the manufacturer looks at C1 and he looks at the table and he gives you the wholesale price. Similarly, he looks at the table and he gives you the production quantity. Once the wholesale price and the production quantity is announced by the leader, then the follower would put those into his response function, as you can see here, and he will give you the order quantity. Similarly, he will give you the retail price. So these are his responses to W1 and Q1. And then this is the period 1 decision. And then, of course, the second period happens. The stage is realized. The C2 is realized as C2. Once C2 is realized, once again, the manufacturer observes C2, looks at the table, and gives you the W2. Again, at the table, he gives you the production quantity Q2. Given these quantities, once again, the retailer looks at his table, and his table, he observes C2, he knows what the wholesale price was announced by the manufacturer, and a Q2 announced by the production quantity, put that into his table, and finds out ordering quantity. So that's the order quantity he gives, and then he also sets the price. So we now have a solution. Given that solution, we can compute the profit of the centralized and the decentralized solutions, and we will be able to see that the solution or the profit in the decentralized setting is lower than the profit in the centralized setting. And in order to achieve the centralized profit, we have what is called the coordinating contract. There are a number of coordinating contracts in the literature, and I will mention two. One is called a revenue sharing contract, one is called a buyback contract. Our focus here is to develop one revenue sharing contract in a 2-period setting of ours. Literature, this is the first time we have a coordinating contract in a 2-period setting in this paper. The manufacturer, here's a revenue sharing contract. The manufacturer proposes a revenue sharing contract with a set of contingent wholesale prices and the revenue sharing rates. So this is a wholesale price here and the revenue sharing rate, and another wholesale price and the revenue sharing rate, where the revenue sharing rates are between 0 and 1. And we can see the phi I is the retailer's portion of the revenue in period I. So here's the revenue sharing contract for our problem. In our problem, as you can see, the retailer's profit is given by the expected value of his share of revenue, which is phi 1 times the revenue minus his cost. And again, in the second period, the same thing. So a coordinating contract is now as follows. For any phi 1, phi 2 in 0, 1, if the manufacturer sets this wholesale price and in period 1 and this wholesale price in period 2, then W1, phi 1, W2, phi 2 is a coordinating contract. We can see that the phi 1 and phi 2 are independent in each period. So manufacturer and retailer can agree on and negotiate over the revenue sharing rates in each of the 2 periods and agree on a contract that is good for both of them, and it will of course eliminate the double marginalization and achieve the centralized profit as a result. The next we go to a continuous time setting, and we go to what is called a cooperative advertising with 2 competing retailers, and we also solve this problem as a feedback Stackelberg-Nash game. This is the paper that is appeared in the proceedings and is written by myself and a co-author, Ganul Selin Savaskan, and in the proceedings you will find this paper. We will not devote too much time to this one, but because we will have another paper to discuss which has another feature that we would like to bring into this keynote. So cooperative advertising is an arrangement whereby a manufacturer pays for some or all of the cost of local advertising undertaken by the retailers for the manufacturer's product. And the participation rate specifies the percentage of advertising that the manufacturer will share with the retailer. Why does manufacturer does that? Because manufacturer wants to sell his product and he's afraid that the retailer will not sufficiently advertise for his benefit. Cooperative advertising has become an important marketing strategy. And as you can see that in 2005, in 1987, $5 billion were devoted to cooperative advertising. In 2000, that figure became 15 billion. There are figures for other years, but we will continue to go further. And the average participation rate is 75%. And as you can see in this table, that there is a different participation rate in different kinds of products. And there are a number of surveys on cooperative advertising which I've listed, and we can sort of see here that IBM gives 50% of the advertising cost, Natural Bounty is 50%, Apple 75%. So the rate at which the manufacturers share depends on the market and industry. And the question that we would like to know is what should be the optimal participation rate? This is the question that we're going to answer in the next 2 papers. In this paper, we have a manufacturer and 2 retailers that are competing, and the manufacturer supports the advertising expenditure of the retailer 1 and retailer 2. And these participation rates are given by theta 1 and theta 2, as you can see here. And XT is the market share of retailer 1, and 1 minus XT is the market share of retailer 2. The dynamics is based on a model that I proposed in 1983 that is called the Sethi model. It is also available in Wikipedia. And this model is as follows. If you remove the player 2, so we'll remove this term and that term, then we have the remaining 2 terms, and the remaining 2 terms says that advertising affects the people who are not buying my product, and this particular product is also, there's an attrition rate, which means there's a decay in market share. So in the Sethi model, there was no competitor, and so only there are 2 terms. But now the competitor is coming into play, so he is advertising to this guy's market share, the first player's market share, and he's also losing his market share to the other one. So if you put all of this together, we have a game extension of the Sethi model, which is used as a dynamics for this problem. And we can have the objective function of retailer 1, which is the margin times the market share, and the cost of advertising times the amount which is not paid by the retailer, and because the theta 1t is paid by the manufacturer, so he only pays 1 minus theta 1t times u1 square. Similarly for the second guy, whereas the manufacturer, his margin comes from both retailers, m1 times xt and m2 times minus xt is his revenue, and his cost is the subsidy that he provides for each of these two guys. So you will subtract those two, and that would be his objective function. Once again, we have objective function of the leader and the follower, and we have a dynamics, and we can solve that as a Stackelberg game. We will then we are now going to a paper that that is just recently published in Siam Journal of Control and Optimization, and the co-authors are Alain Ben Susan from my school, Shaoquan Chen is currently working at Target, and Anshuman Chutani is a professor at University of Nottingham, and Chi-Chung Xu and Philip Yam are professors in Hong Kong. In this particular, the outline of this part of the talk is we will motivate the problem. We will give a brief slide on the literature on the solutions of Stackelberg differential games. These are now called differential games because of the continuous time. We will have a stochastic portion as well. So we will have a stochastic feedback Stackelberg-Nash games. And we will have a game called the mixed leadership cooperative advertising. The static Stackelberg game was already discussed in my initial talk. There's a one manufacturer, one retailer. There was a double marginalization, and the theory of contract, which gives you the coordinating contract. So we will that was the beginning. For this particular paper, we have two research agenda. One is what is the equilibrium concept for a multi-period differential game with both upstream and downstream competition, and we will also find an equilibrium solution of a mixed leadership game of cooperative advertising. There's a literature on the solution of Stackelberg differential games. I will not go into all of these right now, but I will focus on the last paper here, which is done by me and my colleagues, and it's a very recent paper. It was published only last year. And here we will extend the deterministic games proposed by Bashar and Huri in 1984 to the stochastic case. And we will see that the static Stackelberg game at the Hamiltonian level at each instant, and putting all of that together using dynamic programming will give us a feedback Stackelberg solution. And so we kind of unify the Nash and feedback Stackelberg solutions in this paper. The mixed leadership game is the following feature. Each player is leader as well as follower. In some decision, a player leads and the other one follows, and in other decision, the other player leads and this first player follows. And the equilibrium concept we will have will be the same as feedback Stackelberg-Nash solution. And the application we will make is to a cooperative advertising between a manufacturer and retailer. So here's the setup. We have a manufacturer and a retailer. The manufacturer and the retailer, now acting as a leader, announces the participation rates. This guy, M, pronounced the participation rate UM, and the retailer, R, announces the participation rate UR. This is the rate of sharing of advertising expenditure. This is the cooperative advertising participation rate. Given the participation rates, each of the player will decide on their advertising expenditure. R will decide on advertising expenditure VR, and M will decide on advertising expenditure VM. As you can see that both players are leaders and both players are followers. The state of the market share is given by XT, and we will then see the dynamics in the next slide. We can see that the dynamics now is a stochastic differential equation where the change in market share is given by this term, which is the advertising by with the retailer and the manufacturer with some kind of weight which acts on the people who are not buying your product, and there is a decay term. In addition, there is a noise term, there's a volatility, and a WT is a Brownian motion. This is, by the way, very close to the Sethi model in 1983. The objective function of the manufacturer is he maximizes his revenue minus the cost. His cost comes here because he's supporting the expenditure of the retailer, and then he is supporting his own advertising expenditure, but part of that is being supported by the retailer. So that gives us the objective function of the manufacturer. Similarly, we have the objective function of the retailer. Then we define the Hamiltonian, because we are going to solve the game at the Hamiltonian level at each point in time. The Hamiltonian of the manufacturer is margin times X times the advertising cost times the advertising cost, minus the advertising cost. So this is the integrand. And then there's an adjoint variable times the dynamics. Similarly, for the Hamiltonian for the retailer, there is an adjoint variable for the retailer called P sub R times the dynamics. Here, the leading decisions are shown in red, participation rates, and the following decisions are shown in blue as the advertising rates. Given the red decisions, which are the leading decisions, we can maximize the Hamiltonian, and the first order condition is that we take the derivative with respect to V sub m and V sub r, and we set it equal to 0, and we get V sub m and V sub r as a function of UR and UM, which are the leading decisions. We incorporate these decisions into the Hamiltonian. When we go to the Hamiltonian now, the Hamiltonian is given by HM and HR now, and the only variables are UR and UM. Once again, we use the first order condition, and we with respect to UR and UM, and we get the first order condition gives us the optimal UM and UR, or the form of optimal UM and UR in this form. As you can see, that we cannot have a participation rate below 0, so we need to have a boundary solution as well. Now we have now solved the static game using the Hamiltonians at each point in time. We're going to now put all this together into a dynamic programming setup, which in this case means Hamilton-Jacobi-Bellman equation. So now we have a system of Hamilton-Jacobi-Bellman equation where VR is the value function for the retailer and V sub m is the value function of the manufacturer. And these are the Hamiltonian, and these were the decisions that we have already, we know the formula of decisions. The only thing I want to point out, which is important here, is that the adjoint variable of the retailer is nothing but the first derivative of the value function. As we know, the adjoint variable is the marginal value of the state. Similarly, PM is given by VM prime, and so we put that in place of PM. Once we put that, it becomes two equations in VR and VM. These are partial differential equations, which are kind of difficult to solve. As you can see in these equations, UM is given by this, UR is given by this, VM is given by this, VR is given by this. So we have all of these in place. Here is what we do for a solution. We look for a linear value function. This follows from the original Sethi model, and the linear value function. If we can see a linear value function, it can be defined. VRX could be alpha R plus beta R times X, and similarly, we can define the VMX. If we define this, we can compute VR and VM prime and VR prime, and you can substitute that in the previous slide. And then we have three different cases. If beta M is less than beta R by 2, we can see that manufacturer does not participate, but retailer gives the subsidy to the manufacturer's advertising. The next, we have the second scenario in which beta M by 2 is less than beta R less than 2 beta M. In this case, we can see that both people each subsidize the other. Okay. Finally, there's the third scenario in which UM subsidizes, the manufacturer subsidizes the retailer, but the retailer does not subsidize. So we can see that in each of these scenarios, we can reduce the the partial differential equation to a set of algebraic equations. These algebraic equations are very easy to solve numerically. There are no explicit solutions for them, but we can solve them numerically very easily. So the next thing is devoted to a numerical analysis. And since we are doing the numerical analysis, we made the problem slightly more general by adding another term, which is the interactive term, which is k times square root of VR, so Vm. Given that, we can go back to the original system and resolve the problem. And once we have that, we get the system of Hamilton-Jacobi-Bellman equation, which we can solve. So here are our results for solving those equations. As we can see, this particular graph tells you the impact of manufacturer's margin on the participation rates. So here's the x-axis, the margin is increasing, the manufacturer's margin is increasing, and the blue line shows you the participation rate of the manufacturer, and the red line shows the participation rate of the retailer. The red line goes from here and then becomes 0. As you can see, that as M increases, the manufacturer has a greater incentive to advertise more because it is in his interest, because he earns a lot more from the market share, from the sale. And so you can see that up to about this level, maybe around 0.7 or so, we can see that the manufacturer does not support the advertising of the retailer. But at this point, manufacturer started supporting the advertising all the way, and it keeps increasing as M increases. Like, on the other hand, which you can see that if the manufacturer's margin is low and the retailer's margin is relatively higher, then the retailer has an interest in supporting. But as the manufacturer's margin increases, the retailer's support goes down. Eventually, at 1.5, it becomes 0. Because at this point, the retailer is saying, why should I support the manufacturer? Because manufacturer is supporting on his own behalf, and he has an interest in supporting his own advertising expenditure because his margin is very high. So I have no reason to support him. So this is kind of the result that we get. And so the next thing we're going to see is the net transfer of money from the manufacturer to the retailer. We can sort of see here that as margin increases, at the low value of margin, this graph, as you can see, is in a negative territory. This means that there is a net transfer from retailer to the manufacturer. And on this side, we can see that the transfer is from the manufacturer to the retailer. Exactly at this point is the boundary solution where M equal to R and UM and UR both are equal to 0. That means there is no support by anybody and there is no net transfer. So the net transfer by that we mean that since each one is supporting the other, then we can find out the exact amount of money transferred between the two. So this is the other result that we have. And we can conclude finally the presentation. And we have, in this talk, we have delineated the difference between Nash and Stackelberg games. Then we have defined the types of Stackelberg equilibrium in 2-period supply chains. And we have given a general definition of a multi-period feedback Stackelberg equilibrium. We have applied this model to a problem of dynamic pricing, production, and supply chain with cost learning. And we have come up with a revenue sharing contract that will coordinate the 2-period supply chain. Then we go into a cooperative advertising where we discuss 2 different papers. One is a paper with 2 competing retailers, and we solve that as a feedback Stackelberg-Nash game. This paper is appearing in the proceedings of the conference for you to read. And then finally, we have a mixed leadership game of cooperative advertising, which appeared last year in Science Journal of Control and Optimization, and it's available. If you would like, I can send a copy of that to anyone who wants it. And again, we solve this as a feedback Stackelberg-Nash game. Before I conclude the talk, I want to give the list of references that we have. This is a survey paper that I mentioned in the talk. This is the paper of cooperative advertising in pricing and dynamic supply chains. We have a paper by Basar, Ben-Susan Sethi on mixed leadership. And the paper that I mentioned that I gave you, the most recent paper is the paper right below, which is published in Science Journal of Control. And I should thank you very much for letting me present my research to you. And if you have any questions, please feel free to email me at sethi@utdallas.edu. I thank you, and you enjoy the rest of the conference.